So I would like to add a small contribution, so to say, to things we discussed a lot at this conference, which is these Floquet engineered systems and also in connection to topology. So topology and dynamics in Floquet engineered systems. And in our case, we perform this with cold quantum gases, so in these artificial crystals in optical lattices. And I would like to go step by step through this with you because this is with this mixed audience, which is quite nice. So I will remind you on the concept of Berry curvature. Many of you know much better than me, for example, but just to remind you, those who are not familiar with this every day, then I also would like to explain you in detail our system, this optical lattice, which is a boron nitride-like optical lattice, and then to explain to you how we, for the first time, fully measure the Berry curvature, map out the Berry curvature in the full Brillouin zone for this kind of lattice. And then come in the second part to this aspect of this dynamical phase transition, which is debated, highly debated, and you're very welcome to discuss with me whether you believe that this is a dynamical phase transition or not. Okay, we will see. So topology, this first ingredient, we as physicists all know that all these objects belong to the same topology class. So I always think that if you tell children that these two objects are the same, I think they will complain. But you know, for us it's all the same, and a bit more seriously, we all know that topology is extremely important in recent years, especially in condensed matter physics. All these wonderful physics with edge states and the bulk edge correspondence and even up to applications, and no need, I think, to motivate this in this audience. So, but how to describe topology? I mentioned edge states, there is Berry phases, there is bulk edge correspondence, there is Berry connection, all this. So how to describe this? And there's this wonderful word of Berryology, which was introduced by Neil Fuchs and others in this paper here. And typically you can start, in order to describe all these things in topology, by the so-called Berry connection. And this is nothing else. If you have a periodic system, we all know we have our Bloch eigenfunctions, which depend on the band number n and the quasi-momentum k. Okay, and these are the eigenfunctions. And now the Berry connection is that you take the derivative in quasi-momentum space on your eigenfunction and project it back onto your eigenfunction itself, the complex conjugate of this. So how they turn, so to say, in momentum space. Right, and this is the property which contains all the information on topology, so to say, but unfortunately not gauge invariant. So therefore, you build up the curl, and we heard this already a couple of times already yesterday in the nice talk, and you build the curl, and then you get the Berry curvature. And this is gauge invariant property, so you can measure it. So it's so to say how the eigenfunctions rotate around themselves, so to say. It corresponds to a virtual magnetic field or an artificial magnetic field. Right, so this is the Berry curvature, and the nice aspect with the Berry curvature is that you get all the things out of it, like the Berry phase. You know, if you have a Brillouin zone, and you plotted here a Brillouin zone for hexagonal lattice structure, and for example, where a Dirac cone might be here in the center at the gamma point, and if you perform a path in quasi-momentum space, let's say around the Dirac cone, you get a Berry phase, pi in this case, and this is nothing else than, in this case, the line integral over the Berry curvature. Whereas if you integrate over the full Brillouin zone, your Berry curvature, you get the Chern number, yeah, which gives you then, at least for, as we learned yesterday, for the equilibrium case, a non-driven system gives you the number of edge states in your system. So therefore, it is nice, or would be nice, to really see and to measure this Berry curvature in complex systems, because then you have all the information on the topology. Because we will see sometimes it's a bit tricky. For the band structure alone, you cannot deduce all the properties of topology typically. Right, and there have been, of course, many theoretical calculations on Berry curvature, for example, on this boron nitride-like system. These are just few examples. There are many, many more. So boron nitride-like system, which we will study in our artificial boron nitride optical lattice system, on stained graphene, on ferromagnets, and many more examples. But so far, to our very best knowledge, there has been no full measurement of the Berry curvature. There has been measurements on Berry phases in condensed matter, of course on Chern numbers, on edge states, and all these things, but not really on the full mapping of the Berry curvature. And indeed, here it is. This is what we measured last year. This is the full map of the Berry curvature in a Brillouin zone on a boron nitride-like system. And the Berry curvature is here given in false color code and is given in inverse in units of 1 over the inverse lattice vector squared, doesn't matter. And you see there's a lot of Berry curvature localized around this K prime point, which is a massive Dirac cone in this system. And of course, the other ones periodically themselves. And also there is a lot of negative Berry curvature then in this case around the gamma point, where there's also a massive Dirac cone sitting in the band structure. And let me mention also that there is very nice related work, measurement of the Wilson line, very much connected to this by the groups of Emanuel, Bloch and Eugene Demler, Christiane Morris-Smith, and co-workers parallel to our work. So, and now I would like to go step by step with you through this measurement, how we characterize this topology, how we measure this Berry curvature. For this, let me remind you on these optical lattice systems, for those who do not work every day with them. Typically, in most of the labs with quantum gases, there were these cubic lattices. Actually, all this work in cubic lattices started in the 90s with, at that time, laser-cooled atoms. So nowadays, you would call them hot atoms. But many lattice structures were studied there, and Bloch oscillations were beautifully seen, and many other things. And then from the 2000s on, also quantum quasars were loaded in these lattice structure. Typically cubic, which means in a one dimension, you just take a standing wave. If it's retuned, then in the antinodes of the laser wave, where the high intensity is, the ground state of the atom the energy is reduced, and therefore the atoms sees an attractive potential in the antinodes in the high laser intensity, and these are the minima of this periodic potential then. And if you then apply a second standing wave in orthogonal direction, you get a two-dimensional optical lattice, and in the third direction, obviously, then you get a three-dimensional optical lattice of cubic lattice style. And we a bit, to say, pioneered, I think more than 7 years we work now on these non-cubic optical lattice structures, especially we concentrated on triangular and graphene-like hexagonal-like structures. And we studied spin frustration, we studied properties of these graphene-like systems, we studied mod insulator transitions, mixtures of bosons and fermions in these systems, many other things on these non-cubic lattice structures. And the nice thing I would like to advertise, especially in this case for the colleagues from quantum gas physics, that this is a nice lattice structure. You only have to take 3 laser beams, 3 running laser waves, intersect them under angles of 120 degrees, and then this is a very flexible structure, so you get a different type of lattice structures depending on the polarization of your laser beams. So if the polarization of these 3 laser beams, which intersect here and of course interfere and give you then this interference pattern, and if the polarization is perpendicular to this plane, in this case you get the triangular lattice. And the color coding, this is now real space, this is not momentum space, this is real space, and the color coding is such that blue is the minimum of the potential seen by the atoms, and white is our potential maxima. And so polarization particular, you get the triangular lattice, where if you turn the polarization in the plane, then it's a bit more tricky, this interference process, and what you get is then a true honeycomb or graphene-like lattice structure. And then if you turn the polarization out of plane by either 1 or 2 or all 3 of these laser beams, you can fully tune your lattice configuration from, for example, 1D chains to a snake-like 1D chain structure to dimers, isolated dimers also, or also do this boron nitride-like structure, which is, has the same global symmetry, no, not global, but the same principal structure as the graphene-like structure, but where the potential depth is different at the A and B lattice sites. Okay, and also yesterday we learned that there is even this nicer tungsten selenide structure, which is very similar to it, very nice talk. And so we study indeed even a bit more this tungsten selenide lattice structure with respect to the band gaps and so on, but this is a detail. Okay, and even you can realize a square lattice. And I should mention that there is this nice work in the Zurich group by Tillmann Esslinger. They start from a brick-like lattice, so this type of lattice goes the other way around, and can also realize a deformed honeycomb-like lattice. And the work there is very similar work in Tillmann's group. Yes? Is it possible to shake this lattice? Okay, I come to this in 2 slides. So this is not shaken yet. Okay, good point to make this clear, because I also mentioned the Floquet engineering. This is without any shaking, without any Floquet engineering. This is a static structure, 3 laser beams. We have, of course, perfect phase control on all these things. And if the phase is stabilized, that is, and everything is quiet, then this is a static lattice structure. And the change in the lattice structure is realized just by turning the polarization of the 3 laser beams. Okay, and in this case, for the boron nitride, all 3 polarizations are turned by something like 20 degrees out of plane.
So that people were shaking of such lattices may lead to a ring of minima.
Yes, I know. Yes, so we do shake this, and this will be the next step. Yeah, exactly. And indeed, very nice. Yes, exactly. I know that you could also realize a ring. We can discuss later. It's a bit tricky to get a really flat ring. It depends very much on experimental parameters. So, but indeed, it's a very nice idea. So, and the next is indeed what Victor mentioned. Then the next step is the Floquet engineering. But so far, all the 3 first pictures are without Floquet engineering. So, polarization in plane, we get the pure graphene-like lattice. Okay, but typically we start with this boron nitride-like lattice, so turn polarization out. And in this case, I mean here for the graphene, if you look into topology and Berry curvature, the Berry curvature is all focused in the Dirac cones. Yeah, it's divergent in the Dirac cones for a flat, infinite graphene system. Whereas in boron nitride, the symmetry, spatial symmetry is broken, so you lift your Dirac cones, but still these are then called massive Dirac cones, and then the Berry curvature is localized around these massive Dirac cones. Okay, they are still called Dirac cones, even though the characteristic feature, the linear dispersion relation, is missing, which makes them, I would say, really the Dirac, the Dirac part of the Dirac cones. But if it's open, still they are called massive Dirac cones because they have the quadratic dispersion relation then around this point. But from the topology aspect of topology, still you have the phase winding around the Dirac cone, which gives you a Berry phase of pi. Therefore, concerning topology, you know, still they are very relevant. Okay, and if you tune the parameters further, go to a deeper lattice and so on, for specific parameter regime, we tune continuously this boron nitride-like lattice into flat band structure, nearly perfect flat bands. In this case, the Berry curvature is completely washed out. And this is our reference system. This is a bit technical, but it's important for the type of measurement we perform. And so we start typically with the atoms loaded into this boron nitride, then we change the parameters, and then we find all the atoms in this flat, in the lowest band of this 2-band flat band structure. There are of course higher bands, but the nice thing with graphene and boron nitride is these are the two lowest S bands, and the upper P bands are far away, such that the 2-band approximation works really well. And then we do this Floquet engineering. So then we start to shake this kind of lattice. And while this, the nice thing is that we can then break time reversal symmetry because we perform a non-symmetric shaking of our lattice, a non-symmetric driving, which breaks the time reversal symmetry. And then a lot of things get possible. Like, for example, in the nice paper by Victor, to realize ring-shaped structure, and many other topological features can be realized via this Floquet type engineering. I limit myself only to one example here, which is this boron, which is this Haldane-like system for this asymmetric shaking, where we lift the, so to say, 2 of the Dirac or the Dirac cones, massive Dirac cones at the K points, and the K prime points, they still remaining. In this case, you would have a churn insulating state because now you would only have positive Berry curvature in your Brillouin zone, so it would then add up to 1 if you integrate all the Berry curvature here. Okay, and this shaking with the optical lattices, this Floquet engineering was first introduced theoretically by Martin Howelthausen in 2003, and then the first experiments were performed in Ennio Aramondo's group 2007, and similarly also with the Twolevel in Markus Oberthaler's group. And we heard the very nice work by Chen Xin 2 days ago. He pioneered especially the near-resonant shaking, and we did a lot on shaking, especially of these non-cubic optical lattice structures. Okay, and in this case, oh yeah, I should mention, so you get this Haldane-like structure where, depending on the parameters, this is experimental parameters, this is a shaking frequency, and this is shaking amplitude on this axis. And in this, indeed, a small area, only a few hundred hertz wide, we expect to see this Chern insulating state, and all the other area is Chern 0 states. Right. So again, now how do we perform this measurement? So we take potassium-40 fermionic ultra-cold quantum gases, cool them down to quantum degenery 0.1 T Fermi or below, and load them into this lattice structure, create this offset, this boron nitride-like structure, and this flat band structure. Okay, and this is our basis, as I told you, for the tomography measurement I'm going to discuss with you to map out the full Berry curvature. So after this flat band, as I said, then we start this, so to say, Berry curvature engineering, Floquet engineering, or however you would like to call it. And for example, in this case, this is the Andres case, and then we annihilate the massive Dirac cones at the K points and create a new Dirac cone at the gamma point, for example. And this is then the band structure with just a bit of shaking. These are the quasi-energies, the stress states in the Floquet system. And indeed, which is now difficult to see, but in this case you do still have a massive Dirac cone at the K point, here at the K point. And then if we increase the shaking amplitude or come closer to resonance in the shaking, you see we lift this massive Dirac cone splitting here, and then we annihilate this Dirac cone instead. And this is difficult to see. We create the one at the gamma point. So these curves came down here. Yeah? Okay, they come down. And from the band structure, you cannot tell whether this one now is a massive Dirac cone and this no longer, or the other way around. And this is, so to say, a bit the message. From the band structure, it's not possible to get all the information on the topology. Right. So in order to describe now this measurement and how we characterize the topology, it's convenient to describe this in a Bloch sphere representation, and we start with these flat bands. And this is, I come from quantum optics. James Cummings' model is still my favorite system. And it took me some time to go into condensed matter physics, especially in my studies. I never had a condensed matter lecture, so I had to learn what is a Brio and so on. Okay, so I like this system much more, a two-level system. But unfortunately, or fortunately, or interestingly enough, you see it's not just two levels. Here is the quasi-momentum axis K. So, and for each quasi-momentum K in the full Brio zone, this is just a 1D cut, so to say, we have a two-level system. Yeah? We have two bands because it's a good approximation to limit to the lowest two bands. Okay, this is our flat bands. In this case, in the Bloch sphere representation, our Bloch vector, if it's in the lowest band, shows downwards to the south pole, and the upper band to the north pole, and the Hamiltonian is parallel to the z-axis. Then we start the Floquet engineering, so we get this more complicated band structure here. And of course, in this case, if you are at a specific quasi-momentum, let's say this quasi-momentum K here, then if you are in this lowest band, of course, with respect to the original basis states, you are in a superposition of these states, so your Bloch vector shows in a specific direction. And of course, Bloch vector is characterized by, or any kind of vector in a sphere is characterized by two angles, phi and theta. Okay, so if we can get the information for each quasi-momentum on these angles phi, on the position of the Bloch vector, then we have the full state in the full momentum space. Right, and this is, for mathematics, easy. Of course, it's a two-level system, so spin 1/2 system, so can be described by the Bloch sphere representation, by the Pauli matrices. And for each K, it's simple mathematics. You get the superposition of the original eigenstates with these angles, obviously. Okay? And then also the Hamiltonian is given, can be described, written in cosine sine function of these angles. And therefore, it's a simple mathematics. I told you that the Berry curvature is a curl on the eigenstate projection, derivative of the eigenstate projected on the back. So it's nothing else. If you plot all this in, you get this simple formula for the Berry curvature in, so to say, units of these angles. So the only thing we have to do is for each quasi-momentum, for each point in the Brio zone, we have to measure these angles. We have to measure the state. Okay, and this, of course, is a tricky way, and we think it's the very first complete tomography of the state of a many-body system in such a periodic lattice structure. And the idea of measuring it goes back to a paper by Philipp Haufe, Maciek Lewenstein, and André Eckert from 2014, and also from original idea by Garcia-Ripoll and co-workers much older. And we adapted from both of these papers the ideas, so to say, and aligned a bit that they fit to our experimental system, but the idea basically goes back to these two papers here. So we load into these flat bands, and as I told you, for each quasi-momentum, we fill a full band insulator with our non-interacting spin-polarized fermions, okay, in this flat band. And so for each quasi-momentum, in this case, it's turned around because it's a stress state here. The ground state, the lowest band, shows up to the north pole, just for convenience. Okay, I limit myself to one quasi-momentum here in order that I only have to show one Bloch vector then in the following pictures. But we do it then simultaneously for all the other ones as well. Okay, and then adiabatically, from this flat band structure, we start this shaking. Yeah, we do it adiabatically. So a quiet lattice, very cold Fermi, see inside the lattice, and then we smoothly start shaking the lattice. We ramp it up to the amplitude and frequency of this shaking, and we get this hopefully more interesting, more complex band structure, which hopefully might have even more interesting topology, like a Chern insulating Haldane state or whatever. Okay, and for each quasi-momentum now, the Bloch vector turns in the final with the final shaking amplitude and frequency in a certain direction. We have certain states, many-body states here in this system. But it's non-interacting, I have to point out. And how to measure this? Well, the idea here, and this is the basic idea here in these papers, is we just project back onto the flat band. We do the shaking, and suddenly, whoop, we switch off the shaking. Okay, and obviously then, these more complex states are projected back onto the original basis. Okay, and what are they going to do? Okay, now of course the original Hamiltonian is parallel again to the z-axis, so they perform Rabi oscillations around the z-axis. Okay, so the only thing is we have to see these Rabi oscillations between these two flat bands for each quasi-momentum. And this is rather easy to see the quasi-momentum. That is the good thing with the quantum gases, which is not that easy in condensed matter. We simply switch off our lattice, and therefore we let the system evolve, and therefore we get a direct picture of the momentum distribution, of the quasi-momentum distribution in this case, if we quickly switch off our lattice. So here only we switch off the shaking, and then we wait for variable time, and for different time points, always creating a new system, of course, because we destroy the system by the measurement, but we wait, let's say, 100 microseconds and 200 microseconds and so on, and each time we perform a time of flight. And what we then get is this time of flight distribution as a function of time. The color coding is such hard to see, but here I plotted the Brion zone, the position of the first Brion zone, the edges. And the color code is such, this is high atomic density, fermionic density in momentum space, and blue means low intensity in momentum space. And then this movie shows you, if it works, let me see, okay, why does it not work now? Yeah, now it works. Okay, what you see, this is a time sequence, as I told you, and it looks like a mess. Typically you would say, when I saw it the first time, I said, okay, we have to take colder atoms, this is just heating. This is complete rubbish, it's a mess. But it's not, no. If you look in more detail to these quasi-momentum space pictures for different times, here started 6 microseconds to roughly 100 microseconds, and if we follow specific quasi-momenta, let's say this number 1, which is very close to the edge of the Brion zone, to a Dirac cone, massive Dirac cone. In this case, you see there is no intensity here, large intensity, low, and low. Okay, and now if you plot it, measure it in, of course, smaller time space as these 5 pictures only show here extraplurally, you get a very nice Rabi oscillation for this single quasi-momentum here. Very nice data points which are easy to fit. Point 2, the same, there's 3 examples. And of course we can do it pixel-wise. This is taking camera pixel absorption pictures. So to say pixel-wise on our camera, we can work out for about 2,000 points in our quasi-momentum space. Each measure these Rabi frequencies. And the nice thing is we can directly calculate it from this very simple formula that this Rabi frequency fully depends on these angles. These, if I go back, This is this angle theta here, and the initial start angle is the theta phi here. Okay, so and both are directly encoded in the time of flight information. So you see, we get a Rabi oscillation with a specific frequency, which actually depends on the quasi-momentum, but only very smoothly, and we know this and can calculate this as well. And you see the offset phase, where the Rabi oscillation starts. Here it starts at a completely different offset phase as here or here. So this is directly the information on phi, and then the amplitude of the oscillation is directly the information on theta. So for each quasi-momentum, we perform the state tomography via the trick of projecting onto the flat bands.
Why is momentum distribution so broad?
So
broad. These are bottoms, right?
Oh, it shall be so broad. You know, unfortunately, I don't have an original picture. So we start with a fully filled up first Brion zone.
So why don't you do it in momentum resolved?
Sorry?
Why don't you do it in a momentum resolved way?
This is momentum resolved. Sorry, this
right,
is
but then you would make it very narrow in momentum space. Then don't you want to make it narrow in momentum space?
No, because we have in parallel. It's a good point. Here, the idea here is that we do it in parallel for all quasi-momentum. We fill up a band insulating state. Yeah? And this is non-interacting fermions. For non-interacting fermions, it's nice because then they do not interact and you have it all information in parallel. This is the idea. I mean, we could load only one point, but then we get only the information on the local barrier curvature for this one point. Here we do it in parallel. This is the idea. And this is a bit more than just taking one path or so, because we have the full information of the full Brion zone. All quasi-momentum. Yes? Very good point indeed, but you see, yes and no. We know this, we calculated. These are not fully flat bands, as even indicated in my simple PowerPoint drawing. But we can correct for it, and we measure it, and we calculate it. We have a full calculation on all this. And it's a very small effect. It's a few hertz, and it's taken into account in the correction, so to say, on the amplitude here. I mean, but this is very tiny details. So we have this under control. It's a good point. And you also see the timings are not that long. You know, it's up to 200 microseconds. And then, so it's smaller than the oscillation period and so on. Right, it's okay. So, and out of this, so we simply fit the Rabi oscillation for each quasi-momentum and have all the parallel information then, and then plot the amplitude and the phase. So these two kinds are the most important one because this is a full state tomography. This is a picture, a measurement, and we think the first full measurement of the full many-body, non-interacting state of ultra-cold fermions in this periodic system where we have amplitude and phase. And what we then can easily do is perform this formula numerically, which I have shown you, this getting the gradients along x and y direction in quasi-momentum space, numerically, so to say, differentiating it, and out of this we get the barrier curvature. And this is the picture I already showed to you in the beginning, and we can either do it for right-hand circular shaking or left-hand circular shaking. Of course, it's the same, but it's just that the signs of the Berry phase changes and should change if we shake right circularly or left circularly. Okay, and this is a cut through these data along the high symmetry paths in the Brion zone. The data points in the red curve may be difficult to see even. This is theory without any free parameter. Yeah. And also you see here, you could even plot this on top of each other. This is without any free parameters. Of course, we have a bit of noise. We can reduce the noise if we do the differentiating numerically across more points, but then it flats a bit out. We could correct and make even nicer, flatter pictures, but this is really the best of raw data. I like to show the raw data and then all this filtered stuff. Okay, anyway, we have this high resolution, so in the Brion zone to really see all the details in quasi-momentum space, and this is important for the second part, which I will tell you, this dynamical phase transition. Now, if we, as I told you, we could easily, and we have done, a path here around gives exactly pi, so the Berry phase around a massive Dirac cone, and if we integrate across the full Brion zone, we get a very nice measurement of the number 0 with a very expensive experiment. I should tell you this tomography method, in total this picture is 2 days, full 48 hours data taking. Yeah, this is 48 hours continuous data taking. The experiment runs 24/7, and so you see it's a bit of timing, so it's time consuming, and 25 lasers involved, and because we have a Bose-Fermi mixture and all these things, and 3 people can see, but they are not in the lab. They control it from at home. You know, during night they look whether the laser is out of lock, and if they are not too tired or not at a party, they go to the lab and put it in lock again, and then it can continue. Or they let it go and start it again in the morning. So it's different to, I think the older people know other ways of doing experiments in those times with quantum gases. Okay, so what's, okay, this is, and of course, you may ask, okay, he told about topology, but this is trivial topology. Yes, this is trivial topology. Why not then going adiabatically into this Chern insulating state, which I showed you before, the C1, and we tried, of course. And it turned out that you cannot adiabatically reach the Chern insulating state. And there's good reasons. There's this no-go theorem by several theoreticians. If it's fully adiabatic, you start with the Chern zero state. Also with the Floquet engineering, you can, you know, the Chern number is conserved. You need some dissipation, you know. And with the Floquet engineering, you know, the realization of Haldane model and so on. But it is not that easy, we claim, really to enter the state, and we have some good arguments, because to get the tricky dissipation, which means you need cooling into the ground state. You know, you propagate across in this phase diagram, you see a parameter space, and you enter this Chern insulating state. Then you need cooling into this ground state to get rid of this, and it's not that trivial, we claim. Especially to see why there should be cooling, because typically there is indeed heating connected, experimental heating connected to these Floquet engineered systems. Okay, anyway, but what we did is we can easily at least engineer the Berry curvature, even also in these examples all Chern's number is 0, but exactly these curves I showed you in the beginning, if we drive faster or closer to resonance actually, so make more coupling between the bands, the twist bands, then you see you can focus the Berry curvature more localized around the Dirac cones, and it's always this positive and the negative in the center, and this exactly sums up to 0. And also this is all fully consistent with our theoretical calculation, band structure calculations in the honeycomb and the Bohr lattice. Yes? Okay, similar, yeah, then, okay, preliminary with interacting, we see it even more localized. This is the, this is no. Okay, so, okay. The good thing is that, okay, this is about this dynamic topological phase transition. The good thing is most of this I already explained, and Anatoly Prokofiev, of course, did a great job in explaining to us very nicely and a lot this dynamic concept of dynamic phase transition, which I think in this case of 7 minutes I don't have to repeat again, that we have an equilibrium phase transition and the dynamical correspondence, where instead of changing temperature you perform a quench, and then in time you enter the different phase, quantum phase, for example, with the magnetization. And he explained nicely, whereas regularly you have the partition function and the free energy density for equilibrium phase transition. That is the central concept here. You replace complex temperature by time, or you can also say temperature by complex time, however you like to name it. And then you get, instead of the partition function, the low Schmidt amplitude, which is nothing else than you have the usual unitary time evolution of your Hamiltonian system on your initial state. And when this gets orthogonal, for example, to this initial state, then you have 0 in the low Schmidt amplitude, the Fisher 0. And you also can fully parallel define the rate function in some papers called dynamical free energy. And this is then has the nonlinearities in the function of this rate function, which indicates then or should indicate these dynamical phase transition points. Okay, and this all goes back to this very nice paper, Richard Baker, Markus Heil, Anatoly Prokofiev, and Keir-Ein, and okay, these non-analycities. And I told you to mention, I will also not mention, there's meanwhile many more theory work, especially on the Ising model. So this is, I think, is a fruit fly, yeah, of theoretical physics, or the Ising model. So obviously, I mean, a lot of work, but also on the topological systems concerning the dynamical phase transition. I think I skipped this. This is this example. The main aspect is you should see in time an order parameter appears and disappears and appears again. In this case, the spin correlations for an Ising model here calculated by Markus Heil very precisely and so on. So in our case, again, the same system. So fortunately, no need to explain again the flat bands. And we perform the Floquet engineering, but in this case, we do not adiabatically start it, but in this case, we quench into the system. So we load the lattice and we suddenly start to shake already at the final shaking amplitude and frequency directly. So, which of course gives you, if you feel, if you are sitting on these chairs, if these chairs would adiabatically start to move backward and forward or rotate, you would still feel comfortable, yeah, because you can stay in your chair, even if it's then finally heavily rotating, but still you can hold it. But now imagine, boom, I start immediately to shake you. Okay, you can imagine highly excited state, right? And then then we fly, even you lift up with this heavy shaking, and we fly on the ground state chairs, yeah, okay? And then you realize, oh, wonderful, I would like to sit downstairs, but now I even would like to stay in a very nice topological state as you take whatever you think about what the topological state is in this setting here. And you realize, okay, what can I do if I'm so heavily shaked? Can I still get something out of my ground state? Okay, and this is the idea of this dynamical phase transition that, so to say, an order parameter should appear. And we do the same. So this is now, we prepare these flat bands. Then this black line indicates switching on the shaking for some time. And this is now the relevant time. This is the quench here, the quench. And then in this time, we vary this time here, okay, the time after the quench into this churn insulating state in this case. And after each different time, I should have plotted different black lines here, we perform the full state tomography, so 48 hours data taking for each time step here, okay? So we perform the full state tomography. And then what we see, and this always takes time because the picture is so full of information that, yeah, here it comes. This is now the pictures you already know. This is just the phase shown here because the amplitude doesn't change that much. And there's the phase information. After 267 microseconds, this is the time after the quench, you see we still only have the static massive Dirac cones at the K prime and the gamma point. And you see this is the phase in color code. There's a phase winding, a vortex around this massive Dirac cone, as we have seen before in these pictures. And the Berry curvature adds up to 0 in this case. Okay, after 357, still the same wonderful picture, very flat, nothing happens, also very small heating. And then indeed, after something like a 400 plus something microseconds, you see 2 additional of these vortices appear, and they propagate in the Brillouin zone, and they finally annihilate. Okay, I show them these 5 pictures, a bit enlarged here for the back. 2 additional vortices appear exactly. I mean, how would the real churn, Haldane churn insulator with C equals 0 look like in this pattern in the ground state? They would be here around the phase winding, a positive one. Because then we would have positive, negative, but positive, 2 positive would add up to 1. So we would expect here a static phase pattern. Instead, exactly at this position, 2 of these phase patterns appear. Because they are not allowed to develop just one, because it's a quench and then it's a unitary evolution. So the churn number has to be constant. It's still in all this picture is 0. I can show you in the last minus 20 seconds in the next transparency that the Berry curvature still is 0 in all of these pictures. But 2 of these phase vortices appear. Okay, and they propagate out in the Brillouin zone, and then they have to annihilate. Because they know they belong to an experiment in dynamical phase transition where in time you see something appearing and disappearing again. Okay, and then is our interpretation. We call the number of additional vortices, of additional, so to say, dynamical massive Dirac cones, we call this an order parameter. You can debate about it, yeah, but at least what I'm fascinated about, I mean, there could be a complete mess. It's an extremely highly excited state. There could be a complete mess of phase noise of everything. No, at least what they build out is exactly the structure which belongs to the underlying ground state structure, which is this additional dynamical Dirac cone, yeah, massive Dirac cones. But 2 of them, and they propagate. Okay, and we can plot how they. It also takes time. Here we can. So in time, exactly always at the same time. You know, this is always 48 hours. This is 1 week of data. We have in total 4 weeks or 5 weeks of data, so further of these curves. And it's all the same that always at this time they appear and always at twice this time they disappear for different parameters.
Is the work system very phase? Work is very phase?
Yeah, this is indeed, there is a Berry phase. You know, if you plot around one of them, there is a Berry phase of pi. You will see it, but opposite, pi and minus pi. So it's a vortex anti-vortex pair, which is.
And in fact, it's on each of those cones.
Yeah, and in each of those, exactly. For symmetry reason, of course, Berry lattice. You see here those ones, and you see here, and you see here. Yeah, exactly. Yeah. Here I didn't focus on it. We just, to make it more visible. Of course, this is only the relevant point. 1 point in the Brillouin zone due to the symmetry of the lattice structure. Yeah, in each of them they appear. Okay. Okay, this is very nice, and and because this is a dynamic topological pointer, you can talk about it, discuss. I'm open for this, and this is so to say the phase diagram. As a function of time, for which parameter this is the tuning. This is so to say the coupling strength of this near resonant shaking. And you see in this area only here we should expect the Chern insulator. So for these data points, something like these. Okay. And you see they appear for more data points, even outside this region. And as I told you, we have very well control, all independent measurements and characterization. We are pretty sure that this is, from the theory, with very small error bars, the area where we expect the Chern insulating Haldane-like Chern insulator. And we are also have full control on the parameters, so we scan, of course, more. And you see, it's not directly connected. So even outside of the Chern insulating, they already realize there is something closer. And this is what was discussed. There is not a one-to-one correspondence, at least in the appearance of these vortices and the Chern insulating state. But then, triggered by our work, which is on arXiv, and I can tell you we have a lot of discussion with the referees, especially on the name of dynamical phase transition. We all agree it's a nice measurement, but we have a lot of discussion with the referees and on these wordings and the interpretation and so on. Anyway, it's a different story. But triggered by our work, I was in a conference in China and discussed a lot with Hu Chai from Tsinghua University in Beijing on it. And motivated by our work, he published very nice work together with his co-workers on the general aspect of this type of measurements, that it is indeed possible to get the information on the topology out of it, which in the spirit that okay, these additional structures appear, these vortex-anti-vortex pairs, but here they propagate and annihilate. And they do not, in their pathway, do not include the static vortex here. Okay, and he showed in the paper, and then there was by his postdoc a follow-up paper with a mathematically very rigorous proof, I would say, that indeed in all cases, if they propagate, if they include the static ground state topology structure vortex. In this case, you get the linking number of 1, and this linking number is directly a one-to-one correspondence to the Chern number. So if we would observe that our vortices propagate not like this, but propagate like this, okay, then indeed there seems to be a rigorous mathematical proof that in this case we can deduce out of the pathway of these additional topological structures. And I think this is very nice. Topology measurement by topology. Okay, and there is more to come, I think. Okay, but I am running out of time, so I skip this one because we did realize this as well. We see all, this is data, all the Bloch spheres, all quasi-momenta Bloch vectors. There's the top shown on this sphere, and they from the top, they all go down in different directions. They go down, down, down. Okay, and then they here, in this case, they go up here and up to here. And what they have to do is, in the Bloch sphere representation, they have to wind around the South Pole. And if they wind around the South Pole, in this case, we know then we are in the Chern insulating state. Okay, but this is details. And as I told you, yeah, this is maybe the very last wordings that indeed, if we measure the Berry curvature, because we have the full information also in this measurement, and you see around these, they come up here, around these additional vortex-anti-vortex pairs, there is additional Berry curvature coming up. And the system knows it has to stay in 0. So it adds additional Berry curvature here to the center around the gamma point, such that the integral is always 0. So again, a measurement of the number 0 with high precision. But if they would propagate around here, then we would know it's a insulating state. Okay, I would like to discuss the connection to Shenshu's wonderful experiment, because we learned a lot what is the connection to Kibble-Zurach, but I have to skip this, but it's okay, it's wonderful, and that is important, the team, especially to point out, why is it so dark here, I don't know. On my computer they have nicer faces, okay, so we do not work in the dark only, even not when taking photos. Nick, who is really a marvelous PhD student who now graduated, continues as a postdoc. This is really his work, and together with Dominik Vogel and Matthias Tarnowski as a bit newer PhD students, Ben O'Rourke postdoc, and especially to point out Christoph Weitenberg as my senior scientist on this project. We have long-standing collaboration with Maciek, André, and my colleague Ludwig in Hamburg, and the work on dynamical phase transition was done together with Markus Heil and Jan Budisch. And Dirk Sören-Liemann is a senior scientist on the theoretical aspect. He did all the calculation of band structure and these hexagonal structures and so on. And I have some more projects. This was one result on this project here, and we like graphene-like lattices. Okay, thank you for your attention.